different gases. One maybe has oxygen, the other one maybe has nitrogen. Now, if those are each at the pressure of 1 atm, 1 atmosphere, if we put both of those gases together into the same container, and they each kept the same pressure of 1 atm, so now we have the oxygen and the nitrogen. So the question is, would the combination of the two gases, would it be still 1 atm because there are different gases, or would the two pressures combine to make 2 atm? And Dalton's law says that the pressures combine. It doesn't matter that they're different gases. The pressure is determined by the number of gas particles, regardless of whether they are different gases. So since we have added more gas particles both at 1 atm, they combine. And they combine such that they both contribute equally to the pressure. And pressure is determined directly by the number of particles. There's a direct relationship there. So Dalton's law says that the total pressure is equal to the sum of the partial pressures. So we add up the partial pressures to find the total pressure of a mixture of gases. In this problem, it says an anesthetic consists of a mixture of cyclopropane gas and oxygen gas. If the mixture has a total pressure of 1.09 atm and the partial pressure of the cyclopropane is 73 millimeters of mercury, what is the partial pressure of the oxygen in the anesthetic? So this problem might look complicated, but it's really very simple. We have a total pressure and we have a partial pressure of cyclopropane. Call that P1. Now we want to know the partial pressure of oxygen, so we'll call that P2. Now we can list each of those. P total 1.09 atm, and P1, which is 73 millimeters of, and the unknown is P2. So the formula for Dalton's law tells us that P total is P1 plus P2. Now, we do have a problem we need to fix before we can use Dalton's law, however. This pressure unit is in millimeters of mercury, this one is in atm, and so they need to be the same unit before we can do anything. So we could either put them both in millimeters of mercury or both in atm. I'm going to put them both in atm. So the equality is that 1 atm is 60 millimeters of mercury. So for every 760 millimeters of mercury, there's 1 atm. So by 760, and that comes out as 0.096 atm. So now we can continue the problem. We need to solve for P2. So in order to do that, we'll subtract. P total minus 1 is P2. And so P2 then is the total pressure, which is 1.09 minus the partial pressure of oxygen of the cyclopropane, which is 0.096. And so we subtract, and we get 0.994 atm. Now notice that this number right here only goes to the hundredths place. So when we subtract, the rules for sig figs tell us we can only go as far as the least number of decimal places, which would be right here, to the hundredths place. If you line them up, for instance, 1.09, 0.096, if we subtract those, we can see clearly that the least number of decimal places when subtracting means we'll round to the hundredths place. So that's going to come out then as we can round that as 0.99. Okay, let's look at another example, another application. We could also convert this pressure value to millimeters of mercury, and so if we did that, we would come out with, so if we solved it with millimeters of mercury, it would look kind of like this problem. Let me find it here. All right, so you could have also converted ATM to millimeters of mercury and solved it, and then you would have this solution here, and so you'd have 753. Let's look at another type of problem. We're going to use a technique, a gas over water. So picture a situation where we have a reaction going on in a flask. So we have some reaction going on, and it's producing a gas. Now, if we connect tubing to this, and have a beaker with some water in it, and we put a graduated cylinder or some device that will measure volume changes, and we keep the water level up high here, we can measure the volume of the gas that's produced. So there's going to be bubbles of gas going up. Now, keep in mind, however, that at the top of this test tube, so we have a test tube in water, and the gas is going to cause the water level to change inside here. And we can measure that change. We can measure that change in volume. So we have the initial volume and we have the final volume. We can measure that change. Now keep in mind, however, that water evaporates as well as the gas that's being produced is going to contribute. So we're going to have gas coming from the reaction, but also there's a small amount of water vapor that's going to be evaporating as well. The vapor of water that exists above the water container is called the vapor, exerts pressure, which is called the vapor pressure of water. And that combines with the pressure of the gas that's produced to equalize the pressure with atmospheric pressure. So we can measure the atmospheric pressure. We know that that's equal to the total pressure inside of here. Now, part of that pressure is coming from water. So in order to know the pressure of the gas that's produced in the reaction, we have to subtract it out. So essentially, the pressure of gas that we're producing is equal to the total pressure minus the pressure of water vapor. So we're going to use this technique in a lab later on to measure the amount of a gas. But let's look at how we do the calculations for this. A 456 milliliter sample of oxygen gas was collected over water at a pressure 144 millimeters and a temperature of 20 degrees Celsius. how many grams of dry, meaning without water, oxygen were collected. So first our heading there, gases collected over water. So we have this situation where we have a 456 milliliter sample of gas. So that would be this volume here. So that change in volume, we have that volume is the volume it's referring to here. So that is actual total. It says it's of oxygen gas, but more accurately we should say that's the total volume change that's occurring here. We know that that's a mixture of both oxygen and also some water that's being evaporated as well. So the pressure in total, so P total, is 744 millimeters of mercury. So we have all the conditions that we can use to use the ideal gas law, PV equals nRT. And once we use the ideal gas law, we'll be able to figure out from the number of moles, figure out the number of grams of oxygen. But we have to make some adjustments here. For instance, the pressure in total 744, but some of that's being contributed by the water. So we need to subtract out the pressure of the water at 20 degrees Celsius. So we list the information we have. The volume is 456 milliliters. The pressure, which is the total pressure, is 744 millimeters of mercury. The temperature is 20 degrees Celsius. 20 degrees Celsius. We want to know the mass of oxygen. That's our unknown. But in order to get there, first we're going to find the number of moles, or N, of oxygen using the ideal gas law. Now we have a few conditions we need to fix. First of all, milliliters is not going to match the unit of R that we'll need for millimeters of mercury, right? So our R value is 62.4 millimeters of mercury times liters over Kelvin times mole. So that's not going to work. So we're going to need to convert our unit of milliliters into liters. And to do that, we divide by 1,000. So there are 1,000 milliliters per every 1 liter. And so that's just moving the 3 places to the left, 0.456 liters. Now also our temperature value is in Celsius, and that's going to have to match this unit here in Kelvin. So we need to add 273 to that value. So that's going to give us 293 Kelvin. Now the other force is what we had just spoken about, and it's the fact that we need to figure out the pressure of water that's contributing to the total pressure that we're measuring. So the pressure of water, how much pressure of water is contributing to the pressure from the gas. So to do that, we need to know the vapor pressure of water. So the pressure of water is something that varies. The vapor of water varies. So we'll need a table or reference to look that up. And in our textbook, it's one on page 341. And so at 20 degrees Celsius, the vapor pressure of water is 18 millimeters. So that's 18 millimeters of mercury. Okay, so our first thing we need to do is we need to figure out the actual pressure of oxygen so that we can then use the ideal gas law. So we know that the total pressure is the pressure of water vapor plus the pressure of the oxygen. And if we want to know the pressure of oxygen, then we need to that by subtracting total minus the pressure of water to give us the pressure of oxygen. So the total pressure is 744 millimeters of mercury minus the pressure of water, which is 18 millimeters of mercury. And so we subtract and out 726 millimeters of mercury. So this number, that is the pressure of oxygen. And that's the number that needs to be plugged in when we do the gas law in the next step. The next step is PV equals nRT. And so this is plugged in more accurate pressure value for the gas. So we solve for the number of moles of oxygen. N is PV over RT. And now we can plug in, substitute our numbers. So N is E, which is this number, 726 millimeters of mercury, multiplied by the volume, which is the number in the 0.456 liters, divided by the ideal gas constant, 62.4 millimeters of mercury times liters over Kelvin times multiplied by the Kelvin temperature, 293 Kelvin. So that, and that comes out to N is 0.0181 moles. Now there is one additional step here. The problem does ask for the number of grams. So it actually wanted the mass or the number of grams of dry oxygen. So last step then is to convert the number of moles to grams using the molar mass of oxygen. So we have 0.0181 moles of oxygen. And the molar mass of oxygen is 16. But of course it's O2, so it's 2. So for every 1 mole of oxygen, there are 32 grams. So we do that calculation, and that will come out to be 0.57, it's a 5, 0.579 grams of oxygen. I'm not going to take time to do the problem, but I did work this out already. So you can work this out on your own, and I'll show you the solution, and you can see if it matches. So put the solution up right now. So on your own, you pause the video. Here's the solution to number 2. So very similar to the last problem. Convert the milliliters to liters, change the temperature to Kelvin. We have to subtract the vapor pressure of water. That's what I did over here. So the pressure of the hydrogen then is this. We've been to the ideal gas law. Solve for the number of moles. And this problem only wanted moles, so we don't have to go the extra step of the grams. Did we do anything with the equation? Nope, not for this problem. But we could have some problems later on where once you could then do stoichiometry and you could figure out how much of something else theoretically was used up.